Good morning, class. Today we are going to start our notebook entry on electromagnetic waves and electromagnetic spectrum. So we are going to start filling in the page of our notebook that looks like this. And at the top, you'll see that you will be writing some things down that we've already learned about, but maybe you just need to refresh your brain. And also at the bottom, we are going to be writing down some new facts or ones that we're also going to just refresh our brain on. At the bottom, you'll be drawing a picture. So I'll just kind of be walking through those three parts of the first page of notes. So let's get started. All right. Within the room right now, if you look around you, you can obviously see light from the bulbs in the classroom, or maybe there's a door where you can see a window to outside, something of that nature. And that is what we call visible light. But that is only one type of electromagnetic energy wave that we are going to be talking about. There are 6 others. So there are radio waves, which sometimes are broken down into microwaves as well. And then there are infrared rays. We in this room have radio waves and infrared rays in here. Ones that we do not have in here are the ultraviolet, the X-rays, and then the gamma rays. So some facts that we have already learned. Electromagnetic waves do not require a medium to travel. They also are the fastest moving energy waves, even when they are in a medium. They propagate the energy through matter transversely. And just to refresh your brain on that, that means that when an energy wave is moving through matter, it disturbs the matter in a perpendicular direction to the way that the energy is moving. So here is a couple diagrams to kind of show you what that is talking about. Notice that in this diagram up here, okay, with the red and the blue transverse waves, we have blue that is representing electric field. We're going to talk about that more in a second. And then we have the magnetic field represented by the red. So let's get into what that means. Like that all together is an electromagnetic energy wave. So some new information kind of in the middle of your notes. A transverse wave, so as we talked about, we know that that means that matter is being disturbed perpendicular to the way the energy wave is moving. That transfers both electrical energy and magnetism, which is what the diagram on the last screen was just showing. And from way back in the beginning of the year, we learned that electrical energy is actually a form of kinetic energy, which means there has to be something moving, motion of something. And in this case, the thing doing the movement is the electrons. So the electrons are moving. Now don't forget that electrons are just a small subparticle in an atom that have a negative charge. So since they have a negative charge, when they come into contact with other negatives, they might push them away, or if they come into contact with something that has a positive charge, they're going to pull that towards it. So charged particles create an electric field that pushes and pulls on other charged particles. And so that movement of charged particles creates a magnetic field. All right, so also electromagnetic waves move at the speed of light when in a vacuum. And so they actually all move at the same speed. So remember the 7 different types of electromagnetic energy waves I mentioned at the beginning. Those all move at the same speed when they're in a vacuum, which means a place where there is no matter at all, no gas, no liquid, no solid. And that speed is actually 300,000 kilometers per second. So that means in the time that you snap your fingers, the light has gone 300,000 kilometers. And if you think about it, when you turn on the light switch, it doesn't take us very long to see the light. Well, it doesn't take us hardly at all because it travels so quickly. All right. Another, at the bottom of your page, you can do this in whatever way you choose to do it. Perhaps you want to draw a similar diagram, but without all the color and maybe a little less of the detail. But what you want to do is make sure, this is called the electromagnetic spectrum. So you want to make sure that you have the different types of electromagnetic energy in order. And the best way is to do it kind of from left to right the way they have it. So they have it set up radio, microwave, infrared, visible, UV, X-ray, and then gamma. So you want to have them in the same order. And there's 3 important things that you need to have in your notes. You don't have to worry about getting all of the numbers down here. I don't really care that much about those. What you do need to know is the direction of the arrows. So this is telling us that the wavelength of the radio waves is largest and the smallest wavelength would be gamma. So remember that wavelength is a measurement from like crest to crest or trough to trough on a transverse wave. And so radio waves have an extremely long wavelength compared to gamma. The next thing you need to know is that the energy actually increases as we go from left to right. So radio waves do not have that much energy compared to gamma rays. And the last thing you need to know is also about the frequency. And if you notice, frequency is the number of waves that pass each second. So we can tell that gamma rays have a ton of, or has a lot of frequency. So recapping, the wavelengths from left to right get smaller, while the energy being transferred and the frequency both increase. Now notice, we are very accustomed when we say light energy to think about this part of the spectrum right here. And really, that is just a minor part of the spectrum. So we will be studying all 7 coming up soon. So I'm going to let you kind of take like a 2-second break, make sure that you have everything in your notes on the first page, and then we're actually going to go ahead and get started on the next page, and that is titled Electromagnetic Electromagnetic Spectrum. And so that is what you need to have ready to go and take notes. And notice that the left column says important information, and on the right column it says real life examples and application. All right, moving on. Radio waves. A lot of times radio waves and microwaves are grouped together. So on your notes, if there is not a row underneath radio waves that says microwaves, go ahead and group them together. So one important fact would be that microwaves are grouped with radio waves. The next thing is that you need to know that radio waves are listed on the left side of the spectrum, just like you drew on the page before. And they have the longest wavelength, which you already know, but we're putting in writing again. And it has the lowest frequency and least energy of all electromagnetic waves. Now, it's important that you know like real life application of these. So these waves are used for TV and radio broadcasting. So they are picked up by antenna and turned into sound waves. And those are the waves that we just studied. So those sound waves that we listen to on the radio with the bubble were originally from electromagnetic waves, specifically radio waves. Now, this is kind of interesting. If you've ever looked at like the FM and the AM numbers, you might wonder how did they come up with these weird numbers? Well, each radio station in an area broadcasts at a different frequency. So they are, the frequency relates to the number on the dial. So when you see, let's see, like 107.1, that means that is its frequency. But it's not just 107.1. FM is, let me see if I have more information. Yeah. FM is measured in megahertz, which means million times per second. So when you listen to the radio station of 107.1, you are listening to a radio station that broadcasts, the wave will vibrate and being picked up from that radio station 108 million times per second. Now, because of this, because the frequency is so much, we know that the energy, remember how we said that as we move from left to right, we're going to increase the frequency as well as the energy. So since this frequency is pretty high, we know that FM has quite a bit of energy with it. And so therefore, what happens is it goes right on through the ionosphere. If that is a word that you might recall from our atmosphere unit earlier this year, we learned that the ionosphere is kind of like the lower level of the thermosphere, and above that is the exosphere. And exosphere is right on the brink of going into space. So FM stations, we actually lose pretty quickly because since they have a higher frequency and a higher energy level, they just zoom right out of the ionosphere. And when you're driving down the road 50 minutes to an hour, hour and a half, you're going to lose that station that you were currently listening to. Now, let's talk about AM for a minute. Some of your parents or you might listen to 700 WLW. So just to give you a little information about that, this dial AM is 535 kilohertz. Now, kilohertz means 1,000. You might know that from like kilometer. It means 1,000 kilometers. Well, a kilohertz is 1,000 hertz or 1,000 waves per second. So even though the numbers, when you look at that dial and it says 700 WLW, you're thinking, oh, that's a big number compared to like the FM station of 107.1. However, it's not million times per second, it's 1,000 times per second. So these waves do not have as much energy and frequency, and so therefore, when they hit the ionosphere, they do not have enough energy to make it through the ionosphere, so they actually bounce back down. Now, interesting enough story, during World War II, this is actually how Europe found out what some of our plans were, because we were talking on 700 WLW, talking about our military strategies and what was being discussed and all that. And Europe was actually picking up our signal because it's being broadcasted up and then bouncing off the ionosphere and right back down. So if you've noticed, 700 WLW can be picked up a lot around this country. If you've been on a road trip and you've been able to tune in whenever you want to hear Reds game or whatever, it's because it does not make it through the atmosphere, so it bounces off and we are able to receive it in many different areas around the country. So that's radio waves. Now, some of you might be asking yourself, well, what's the difference between XM? And this is something that we will continue talking about tomorrow. So hopefully you have at least the first page and radio waves filled in at this point.